Now that we have the unit circle, we can fully define the trigonometric functions. And this is all based on the unit circle, really based on sine and cosine. So let's look at sine of theta first as a function and consider it on the unit circle, right? For an angle of 0, right, this is the angle is how far it's open from the y-axis. And for an angle of 0, this is where we're at. And on this point, right, we are at point 1, 0. So sine of 0 is 0. And then as we increase angle, so as angle gets larger and larger, until this point here, you can see that the y coordinate is getting higher and higher and higher until it hits 90 degrees. 90 degrees has a y coordinate of 1. So as theta increases from 0 to 90 degrees, or pi over 2 radians, sine theta increases from 0 to 1. And then as we increase further from there, keep going further and further down. So this angle, then this one, and all the way to the straight angle, you can see that the y coordinate is decreasing down. At this point, it's going to be at 0 again. So from pi over 2, 90 degrees, to pi, which is 180 degrees, sine of theta decreases from 1 to 0. And of course, from here you can see that we're going around the circle again. The y coordinate goes from 0 to -1 at this point, and then we're going to go up from -1 to 0. So from pi to 3 pi over 2, we go from 0 to -1. That's this third quadrant. And then finally from 3 pi over 2 to 2 pi, we go from -1 to 0. That's how we can move around with sine. Of course, sine theta then restarts. At this point here, once we go all the way around, we're at 360. And now if we increase further, well, we're just going back around the circle, right? We're just going up along the circle to this point, and that's going to be from 2 pi to 2 pi plus pi over 2. And then you can keep going around this circle, this circular pattern. The same thing happens for cosine. Cosine is the x-coordinate, so we start here at 0, 1, or sorry, 1, 0. So the x-coordinate starts at 1. Then as we increase the angle, right, up until this point here, this point is at 0, 1. So now you can see that the x-coordinate went from 1 to 0 in this first quadrant. Then it goes from 0 to -1 in the second quadrant. Then it goes from -1 back to 0, going along this angle, and then going along these angles, we're going back to a x-coordinate of 1. So using this idea, using this pattern, we can graph the equation, and this is what we get. For sine of theta at an angle of 0, we have 0. Then as we go up to here, this is pi over 2, or 90 degrees. It goes up to 1. This is at 1 here. Then we go back down to 0 at pi. Then at 3 pi over 2, or 270 degrees, we go to -1. Then we go back up to 0 at 2 pi. So that's the wave that it went through. That's the motion. And for cosine, right, we have it was at 1 in the very beginning. Then it went down to 0 at pi over 2. Then at pi, it went down to -1. Then back up to 0 at 3 pi over 2. And then 2 pi. And then, of course, it repeats. Both of these things repeat every single 2 pi. So it's going to go the same exact pattern. Go up, then down, then up. And it goes backwards as well. It follows this same exact pattern that we had backwards and forwards, because it just keeps going around the unit circle indefinitely. And these do pass the vertical line test, so we do know that they are functions. The domain of these functions, well, for sine, you can see that it continues indefinitely to the left and to the right. So the domain is everything. You can plug any angle you want into a sine function. The range, however, is limited. You can only go from -1 to 1. The same is actually true for cosine. Any angle is fine, but the range is limited to -1 up to 1. Now for symmetry, this is actually interesting because sine, I can flip this 180 degrees around the origin point. So just rotate around that point. And you get the exact same thing. So sine is odd symmetry. In other words, sine of negative theta, for instance, this one here, this is -1. This is at -pi/2, is the same thing of negative sine of theta. So this is going to be -1. If we put the negative of that, that's what we get when we plug in this one. So the negative of -1 is +1. For cosine, you can flip this over the y-axis, and you get the exact same thing. That is even symmetry. And this really means that cosine theta equals cosine of negative theta. That's just even symmetry. Now, graphs that look like these things, that look like the sine and cosine functions, are called sinusoids because they are special graphs. They're so very useful in life, and anything that moves like a wave looks like a sinusoid. Sinusoids always have an amplitude. And this is really the idea of the height from the midline. So here for sine and cosine, both of these have a midline right here at 1. That's where they always kind of like revolve around. Or sorry, 0 is this line. This is y equal to 0. And from this, you can see it has a height of 1 and a depth. You could say -1, but it's really a distance of 1. So that's what the amplitude is. That's how you find the midline. So the midline here is right in the center, y equal to 0. It has a height of 1 and a depth, a distance of 1. That's the amplitude. They also have a period. And for our periods, for these basic sine and cosine functions, the period is 2 pi. So it's 2 pi periodic. That's the way we say it. Every 2 pi, we start here at 0 and we go up to 2 pi. This behavior repeats itself. And you just cut this section out and you can just keep repeating that. You can see that right here. This is again, goes up, down, up, up, down, up. It's the same behavior over and over and over again. Look at it on a graph and zoom all the way out, zoom to the left and to the right as much as you want, and you'll see this exact same behavior. The same thing is true for cosine. If we start at 0 and go to 2 pi, this behavior here where you go down, then up, you can see right here as well, down, then up, and we continue down, then up, and so on. In fact, you don't actually have to take these sections out. I could actually take this portion up to this portion. This is 2 pi right here. And you can see this again, right? This is going to be right here. So it's the same exact behavior in both of these portions. And you can do the same thing as much as you want. For any 2 pi portion you look at, you're going to see that the function just keeps repeating itself to the left and to the right. That's what a period is. Now, the phase shift is how much the function is shifted left or right from the norm. And the norm, of course, being these sine and cosine functions. These parent functions, of course, they're not shifted at all. But it is important to note that really sine and cosine, if you just look back up here, sine and cosine are just phase shifted off of each other. If I took this graph at this point and moved it this way to here, you're going to see that this point's going to be right here, and it's going to go down, then up, then up. That is the exact same thing as this. which means that if I just phase shift sine backwards by, this distance here is pi over 2 or 90 degrees, I get cosine. And the same thing is true the other way. If I take cosine, I take this point and I move it forward by pi over 2, then I get, say that would be up, then down, then up. But this behavior is right here. So cosine is the same thing as sine, but phase shifted forward by pi over 2. So really, sine and cosine aren't different wave functions. They're really the same thing. They're just phase shifted off of each other. Okay, now the tangent function is an important one, and it's really defined using sine and cosine. In the unit circle, the basic unit circle, we saw that tangent of theta equaled y over x, and y was the same thing as sine, and x was the same thing as cosine. And so really this is the same thing as sine over cosine theta. That's one of the basic definitions of tangent. And if you were to graph this, you get this interesting behavior here. Cosine can equal 0. And whenever it does, you get these asymptotes. And so it's important to know where cosine equals 0, that's where you're going to have these lines. And tangent will always shoot downwards, to the left, upwards to the right. And it repeats this behavior over and over again. It has a period of pi. That's this distance here is pi across. It just keeps repeating this indefinitely to the left and to the right. Now, within these points, there are some important ones. First off, every pi over 4 is an important point. Of course, when you have pi over 2, there's the same thing as 2 pi over 4. You have an asymptote. So this is going to be at every, see, pi over 2 is 90 degrees. So that's going to be at 270, 90, negative 90, negative 270, and so on. Pi over 4 here, this point actually goes down to here. And that happens at negative 1. That's negative pi over 4. And at positive pi over 4, we have positive 1. That's because at pi over 4, sine and cosine, this is at 45 degrees, sine and cosine equal root 2 over 2, and the cosine of pi over 4 equals root 2 over 2. So sine divided by cosine, it's the same thing divided by each other. That's just 1. And similarly for negative pi over 4, in that case, sine is going to be negative, so you get negative 1 instead of positive 1. And of course, right here at 0, and then here at pi, here at 2 pi, negative 2 pi, those always give you 0 for tangent of that angle. Okay, the domain of this is going to be everything except for the asymptote. So I could say x element of r. I could write it like a interval, but it's going to be kind of weird. This thing is a little bit easier. X element of r, except that x cannot equal really where the vertical asymptotes are. And I said here that every vertical asymptote happens at pi over 2 plus k pi. It's a periodic thing, so you have to write it this way. K is just an integer, so you can choose any integer you want, and that will be a vertical asymptote. There are infinitely many integers, so there are infinitely many asymptotes. And so all I have to really do here is, I should say theta. Theta is an element of r, where theta does not equal pi over 2 plus k pi, where k is an element of the integers. So that's a way of saying it's everything except for these pi over 2, the 90, 270, negative 90, negative 270, and so on from there. The range is everything. You can see it goes downward towards negative infinity, up to positive infinity. The range is nice and easy. There is symmetry here, right? If I rotate this about the origin by 180 degrees, I get the exact same thing. And each one of these things would flip over to this one. So this one over here, this point right here flips over to this point. This point here flips over to this point, and so on. So there is odd symmetry in this case. And the period, as I said before, this is pi periodic, not 2 pi periodic. That's the important distinction here, is that here we have a period of only pi. So it's pi periodic. Okay, so that was the first 3 trig functions, sine, cosine, and tangent. But of course, we also look at the reciprocals of those. And so cosecant and secant really are defined by sine and cosine. So to graph these things by hand, if you were to do that, what you would want to do is instead don't graph cosecant, just graph sine. And that's what I have here. I have graph sine. And when you flip this, that means whatever sine is 0, in this case, it'd be right here at the origin, right here, right here. There's infinitely many of them. Well, you're going to have 1 over sine, right? Because cosecant equals 1 over sine theta. And if you have a 0 for sine theta, then that means you have an asymptote. So there's always going to be these asymptotes here. And that's the importance of drawing sine theta, or if it's transformed, then you can just graph cosecant quite easily by finding the asymptotes. And all you have to do is find the peaks. They touch. The peaks of sine and cosecant, they touch. And then this thing just asymptotes to the left and to the right, because there's going to be asymptotes bounding those these parts. So this valley here touches there, and it goes down like this. That's a basic idea of how to graph cosecant by hand. And the same thing is true for secant, right? Secant is just 1 over cosine theta. So if we draw cosine theta, that's what this blue line is here, then you can see where when it equals 0, that's going to give you your asymptotes. And the peaks and the valleys touch. So this one goes up and up. This one goes down and down. And for both of these things, you can see that it has a period. As a period of, well, where's the repetition? This thing and this thing repeat, which means this is our period. This is our period. This one here, and then this one here is our period. And those are over a period of 2 pi, just like sine and cosine are. You have to go through this whole 2 pi period before it repeats itself. It's up here, now it's up here again. So that's where the repetition happens. So it's 2 pi, and then the same thing over here. This one's a little bit off, but that's fine. This is 2 pi. And then I don't have it drawn here, but this would be the next one. This is where that goes up to. That's again 2 pi. So cosecant and secant have the same period as whatever sine and cosine functions they come from. The domain is going to be everything except for when we have asymptotes. And that's going to be, for this first one, right, we had asymptotes at every pi, 2 pi, pi, 2 pi. So except for theta cannot equal pi k, for k equal to an integer. And so when k is 0, you get 0, which is an asymptote. When k is 1, you get an asymptote here, because that's going to be k times pi, which is just pi. That's what that is there. That's an asymptote. When k is -1, you get negative pi. That's an asymptote. When k is 2, you get 2 pi, an asymptote. K is -2, you get -2 pi, an asymptote. So on and so forth. The range is going to be everything except for this middle portion here, right? This portion, it does hit this point. It does touch the valleys, but this portion here is going to be from -1 to 1. So it's going to be everything except that portion. And this has symmetry. I can flip this 180 degrees. Rotate 180 degrees, and you can see that it is odd symmetry, which makes sense because sine is has odd symmetry, so cosecant should also have odd symmetry. Similarly, for secant, it's nearly the same kind of stuff for domain and range. The domain is going to be everything except, in this case, it's not going to be the pi. It's going to be on, this is negative pi over 2 and pi over 2. This is going to be 3 pi over 2 and negative 3 pi over 2. And so for that, we have pi over 2 plus pi k, where k is an integer. So for, k equal to, let's say, 2, right? Or let's do negative 2. Negative 2 pi plus pi over k, that's going to be negative 3 pi over 2. It's going to be pi over 2, negative pi, negative 3 pi over 2. That's right here. So this was at k equal to negative 2. And you can find all of the asymptotes from each one of these things. So that's what theta cannot equal. Okay, the range is going to be the same thing as it was for cosecant. And you can see that this symmetry is reflective across the y-axis. This is even symmetry. Cosine had even symmetry. Secant is going to have even symmetry. The last one we're going to look at, of course, is cotangent. That's the flipped version of tangent. And it looks very similar to tangent. It's been flipped. Tangent actually looks like this. It has asymptote here and here. And it goes like this. That's what tangent looks like. So you can see that cotangent has been pretty much flipped 180, but then phase shifted off of the normal tangent behavior. So it does act a little bit differently, but really has the same kind of period, pi periodic. It's going to have different asymptotes, but it still has these asymptotes every pi, certain distance from every pi. And it's still going to have these important points every pi over 4, because tangent had the important points there, so cotangent will also have these important points. I can show that here. This is going to be pi over 4. This is going to be pi over 2. This is going to be 3 pi over 4. Pi over 4 goes up to positive 1. Pi over 2, of course, is 0, and 3 pi over 4 is at negative 1. All right, the asymptotes happen every k pi. You can see here at 0, when k is 0. When k is 1, you get 1 times pi is pi. When k is 2, you get 2 times pi is 2 pi. Negative 1, negative 2 for k. So the domain is going to be everything except for when we have k pi or k as any integer. The range is once again everything, just like it was for tangent. Symmetry, if we rotate this, around the origin by 180 degrees, see this point here is going to go up to here, this point to here, and so on. You can do that for every single point. This is going to be odd symmetry. Tangent was odd symmetry, or had odd symmetry, so cotangent also has odd symmetry. The period, once again, it's pi periodic.